So good morning, everyone. Today's short video is sort of going to be a wrap-up and a review of a few things we've already done with respect to stereochemistry. One of the things I'd like to spend a few minutes on is assigning R and S again. Because we did that back almost 2 weeks ago now, but a little bit of a review. I know there were a couple of questions in class about it. So for example, what if we had a molecule like this? Okay, something that looks like this. Okay? We clearly have a chirality center here. We have a methyl group, an OH, a bromine, and a hydrogen. So that's 4 different groups bonded to a single carbon. So we should be able to assign priorities to these and then give it an R or S designation. So again, it's atomic number, right? Bromine is 35, so that's going to be A. Hydrogen's number 1, that's always D. We have oxygen and carbon, right? Oxygen is, what, 8 up there, so that's going to be B. Carbon is 6, that's going to be C. Okay, so we've assigned our priorities. But notice in this molecule, my D group here, my hydrogen, is not back as it's supposed to be based on the definition of how you assign R and S. And it's also not in front either. It's flat in the plane of the chalkboard. So if that's the case, you cannot assign an R or S to this molecule just as it is. You are literally going to have to take the molecule and rotate it so that the hydrogen is in back in order to be able to make an assignment. Okay? So what I would suggest you do is hold on to this methyl group, right? And then simply rotate the other 3 groups around. So if this hydrogen needs to go in back, this bromine will come in front, this OH will swing around and be flat over here, right? So I'm literally going to rotate around this bond. I'm going to hold my methyl group. So what I end up with then, and that's not changing the molecule, that's simply rotating it, right, around a single bond. I'm then going to have my OH in the flat spot, that came down, hydrogen went to the back, and the bromine ended up coming to the front. So again, I've rotated these 3 groups around to get it into a place where I now can make the assignment. And it's still the same, this is B, this is A, this is B, this is C. Okay, and again remember, it's A to B, B to C. It does not matter about this D group. I start at A and go directly to B. D may or may not be in between. That has nothing to do with it. So A to B, B to C. Okay, so that is counterclockwise, so this is going to be S. Okay, and that's going to be S. And if we look at the molecule here, we only have 2 carbons with an OH. So this is going to be ethanol. Right, for 2 carbons with an OH, and on carbon number 1 here, there's also a bromine, so that's going to be 1-bromoethanol with S would be the full name for that molecule. So again, if this D group is not in back where it's supposed to be, and it's not in front, you cannot assign this way. You must get it to be in that back position first, then make your assignment. Okay, so that might cause some confusion for people. Another one is a slightly different way to draw enantiomers. Okay, so a slightly different way to draw enantiomers. So if I had just a very simple molecule, let's go back to where we started. And go back to that 2-butanol. So this is 2-butanol. And again, this is going to be our A, that's our D, carbon-carbon, but this is the bigger group, that's BC, so ABC. This one is going to be R, 2-butanol. Okay, doing the quick assignment there. Now, typically, you would draw the mirror here and then draw the mirror image, right? And that would be the other enantiomer. And that's how it's defined. But what if I did the following? Right? I draw the molecule that looks very much the same, so that's not technically the mirror image. I didn't put a mirror up here. But look what I did. I simply switched the position of my H and my OH. Okay, so now the OH is back and the H is up instead of over here. Well, if we do our assignments, there's A, there's D, there's B, there's C. So again, A to B to C is still clockwise, but now look where my D group is. It's in front. So I switch my assignment. So this is, in fact, S, 2-butanol. So drawing the mirror image is probably the easiest thing, right? Because that's how it's defined. But certainly if you simply switch the 2 groups, right, and leave the rest of the molecule the same, you also get the enantiomer. So sometimes in the book and other places you'll see it done this way as well. So where you don't actually draw the mirror image, you just switch the two groups. And we talked a little bit about that in class on Monday as well. Okay, so a different way to draw the two enantiomers, switching the two groups, the H and the OH. Then the last bit of review is going to be about Fisher projections. Because again, these tend to be very difficult, right? So I'll draw a couple of Fisher projections here. And so let me show you the two molecules, right? There they are. So this is going to be a 2,3-dibromobutane, for example, where the orange ones are the bromos, right? So if I put my hydrogen here, so this is the actual molecule, I have my bromine here, my hydrogen here, my bromine here, and then my methyl on top and on bottom. And now I literally am going to draw the mirror image, right? So bromine and hydrogen and bromine, methyl up here, methyl down here, right? So there's the two mirror images of each other. So now the question is, are these the same molecule? Are these enantiomers, right? That sort of thing. So if you're dealing with Fisher projections, remember this. The horizontal groups are the ones that are out toward you, okay? The vertical groups, the one on the top and the bottom, are back. That's the definition of what a Fisher projection is. So if I want to try to decide if these two are the same or are enantiomers, I can take this one and literally slide it over and try to place it on top of the other one. And there you will see that the bromines and H's do not match up, okay? The other thing I can do is I can spin it 180 degrees. Okay, so spin it 180 degrees and then try to line it up. And once again, you see the H's and bromines do not line up. Okay? What I cannot do is flip it this way. Because now look what has happened. Right? So I've just taken it and flipped it around. The horizontal groups are now back toward me. That is no longer a Fisher projection. Okay? If you spin it this way, that is not a Fisher projection. That is not allowed when you're trying to decide if they're the same or enantiomers. You can literally move it over, or you can flip it 180 degrees, but you've got to leave those horizontal groups out toward you. You cannot turn it this way and try to see. Okay? That simply does not work. So these two, it turns out, would be enantiomers. Because clearly they're mirror images, right? These are the two chirality centers, right? And based on me trying to sort of flip them and move them, they're not the same. Okay, so that's a Fisher projection thing. So for things that are not in the Fisher projection, you can move them any way you want. But again, Fisher projections, you can either slide it directly over, or you can go 180-degree turn and then slide it over, but you cannot flip it around this way, okay, because that changes the positions of the groups and it's no longer then defined as a Fisher projection. And so that may cause a little bit of trouble as well. And then last but not least, there is a section in the chapter, we're not going to do much with it, that talks about how you can separate enantiomers. So what if I had a racemic mixture, a 50-50 mixture? Right? And what if I want to separate those and actually get the two enantiomers into different flasks or different beakers? It turns out that's an extremely difficult thing to do. Because remember again, enantiomers have all the same physical and chemical properties with the exception of that rotation of light, which we'll deal with in lab this week. But that doesn't help me in separating them. So in order to try to separate them, it's a very, very complicated process. What I need to do is take my enantiomers, and I need to do a chemical reaction to them. And in the process of doing that reaction, I make them diastereomers. So they're no longer mirror images of each other. Once they're diastereomers, now they have different properties. I can then try to separate the diastereomers. Once I've done that, I need to do another chemical reaction to remove all of that stuff I added to get back to my original enantiomer. And at that point, hopefully, I should have them separated into two different flasks. So I need to react the enantiomers to make them different molecules that are diastereomers, then do the separation, then do another reaction to try to remove what I added in the first place to get back to the enantiomers. Again, that's a very difficult and complicated process, and it's really one that you do not want to do if you don't have to, right? So ideally, you would either try to isolate the compound of interest from a natural source, which typically would give you only one of the enantiomers, right? Natural trees and other living organisms tend to only produce one stereoisomer. So you could do that. You might be able to get the reaction through some enzymatic pathway. Again, enzymes are very specific, right? Bioreaction sort of things, so that they'll typically only make one molecule or one enantiomer. So there are some other ways to go about it, but trying to separate them, actually physically take that 50-50 and get them in two separate flasks is extremely difficult and something that you just are generally not going to want to do if you don't have to. Okay, so we'll pick up a little bit of this. We'll do a few last examples of assigning R's and S's and looking at some other things in class on Wednesday in anticipation for the assessment on this chapter Friday. We'll see you all Wednesday.